In part 1, we built a convolutional neural network in a spreadsheet. It has the structure shown here. The input layer feeds into a convolutional layer. That convolutional layer identifies horizontal, vertical, and diagonal lines in the image. That feeds into a max pooling and activation layer, which shrinks the image by picking out the important parts. Finally, that was fed to a fully connected layer that made the final decision. We set the weights in this final layer to effectively add up all the diagonal lines and compare it to the sum of the vertical and horizontal lines. If there were more diagonal lines, it would indicate the image was an X. If there were more vertical and horizontal lines, it would output a T. And because we were only comparing X's and T's, this worked fine. However, if we want to also have our network handle an L, that approach won't work. Both L's and T's have horizontal and vertical lines, so our simple comparison isn't powerful enough to tell them apart. There's a few adjustments we could make to accommodate an L. I'm choosing to add a second convolutional and max pooling layer so we can see how multiple convolutional layers build off of one another. This architecture of multiple convolutional layers is commonly used. This figure is shown from a paper about classifying clouds and shows a model with 4 such layers. And this is the architecture for AlexNet, which did very well in general image recognition in 2012 and kicked off a wave of new research into applications of convolutional neural networks. Notice it's made up of the same building blocks we've been playing with, convolutional layers and max pooling layers. For me, understanding how these later layers build off of previous ones was a bit of a sticking point mentally. It wasn't until I built the spreadsheet that it really clicked, and hopefully the process gives you that insight as well. To make this concrete, let's design a feature that recognizes the letter X. After our first convolution and pooling layers, we have this pattern of activations. Remember that each box is a neuron, and the more red it is, the higher its activation value. The distinctive part of an X is the 2 diagonal lines crossing, so let's focus on those 2 features first. We, the humans, can see that the crossing happens here. We'll want to create a set of 4 feature kernels that will be activated in this location and locations like it, where the diagonal lines meet. We could make these kernels of any size we like, but 3 by 3 will work fine. The important part from diagonal 1 are these 3 neurons here, indicating a strong diagonal line up and to the left through the central neuron. Therefore, we'll have our feature respond positively to those neurons. I did some experiments and found that 0.33 seems to work fine. Similarly, the important neurons from diagonal 2 are these 3 neurons, corresponding to a diagonal line up and to the right. The rest of the neurons in each of these kernels are not helpful in finding an X. And as we saw when exploring convolutions, we'll want to have the sum of all terms in the kernel be less than or equal to 0. To accomplish this, we'll fill in the rest of these cells in these 2 matrices with negative 0.17 to make the entire sum slightly negative. For our other 2 features, we'll fill in those kernel matrix cells with small negative values. Neither horizontal nor vertical lines indicate an X, so the more horizontal and vertical lines we see, the less likely we're looking at an X. All filled out now, these 4 kernel matrices make up our feature that detects an X. Next, let's look at the T detecting feature. The key difference between a T and an L is where the horizontal and vertical line meet. Again, we the humans can see that the vertical line intersects a horizontal line near the middle of the horizontal line. To encode that, we'll use a positive value in these cells to correspond to these parts of the vertical kernel. Again, through experimentation, 0.33 works well enough. For the horizontal part, we'll want to respond positively if our neurons have detected horizontal lines in any of the spaces at or above our neuron of interest. And since there's more of them, we'll use a smaller weight. To balance out the total weight of our kernel, we'll add in some negative values in these other cells. And since T's don't have diagonal lines, we'll slightly penalize all of the diagonals. Finally, for the L, we'll try to encode a horizontal and vertical line meeting at their edges. We'll have our neurons be excited if these horizontal and vertical values are activated from the first layers. Those indicate the type of connection that we see in an L. As before, we'll put negative weights in the remaining slots to balance out our kernels and ignore the diagonal lines. With these features figured out, let's go implement them. This link has the template partially filled out with the first 2 layers. Here on layer 3, our second convolutional layer, we have space for each of our 3 letters. Each letter has its 4 kernels. To compute the convolution for this cell, we'll add together 4 sum products. For the first sum product, we'll use the upper 3 by 3 from feature 1, and the first kernel. Then the second sum product, we will use feature 2, and the second kernel. We'll repeat this process for the remaining set of feature kernels. We'll implement one more max pooling layer using ReLU to remove the negative activations. We'll use a similar formula as we did previously, using offset, row, and column to allow us to drag the cells without using overlaps. The fully connected layer at the end is very similar to the earlier network. We'll use sum to add up all of a given feature from layer 4, basically giving them all the same weight. The weights we give per feature will be pretty straightforward. We'll positively weight the T feature for the T category, and the X feature for the X category, and so on. Then we'll use negative weights for all other features, and 0 for our biases. One last use of the sum product will compute our weighted sum of the features and weights. We'll compute 3 exponentials as part of our softmax activation function. Normalizing the exponentials by the sum will finish up the softmax, and our convolution network is finished. Feel free to copy and paste the example data from the README page into the input to test it out. Before we talk about how to build and train a network in real life, I want to briefly show another way of visualizing the network using 3D shapes of neurons. This type of diagram shows up in the literature, blog posts, and some tutorials. They took me a while to really wrap my head around it, but once I did, the visualizations became very helpful. We picture the input layer as a 16 by 16 by 1 rectangular prism. After the convolution layer, our prism of neurons changes to 14 by 14 by 4. The convolution itself shrunk the dimensions due to it trimming off the borders. The prism gains more depth as we increase to 4 channels because there are 4 features. We ended up with 36 weights because each feature had one 3 by 3 kernel, and one kernel because there was one input channel. The kernel stride being 1 just means that we slid it across the input without skipping any spaces. The pooling layer halves the dimensions of the prism. We pooled a 2 by 2 square using a stride of 2 to avoid overlaps, and this resulted in a 7 by 7 by 4 prism of neurons. The second convolution only has 3 output channels because there are only 3 features. However, each feature requires 4 kernel matrices because this layer has 4 input channels. Again, the dimensions shrink from 7 by 7 to 5 by 5 because our convolution trimmed the border pixel off. The final pooling layer halves our prism of neurons dimensions again before feeding into the final fully connected output layer. We had our network detect 3 distinct letters, so each of our 3 output neurons is connected to all 27 neurons from the previous max pooling layer and has a bias. Suppose for a minute that we wanted our input images to not be grayscale. That is, we wanted them to consist of red, green, and blue pixels. We would change our first layer to be a 16 by 16 by 3 rectangular prism with one channel for red, green, and blue. We would update our second layer's features to require more kernel matrices. Those features now have 3 inputs, so we need 3 kernel matrices. The size of the convolutional layer's rectangular prism of neurons doesn't change. In fact, the rest of the network doesn't need to change either. Now suppose we want to have our network detect more combinations of the basic lines. We can have that layer look for 8 features instead of 3. This increases the number of weights in that layer, increases the number of neurons in the max pooling layer, and the number of weights in the final layer. Finally, suppose we want the network to detect 26 letters instead of just 3. This is achieved by adding 23 more fully connected neurons to the last layer. Each of those neurons will look at all 9 neurons for each of the 8 features in the previous layer and a corresponding bias. With this understanding of these volumetric visualizations, you should be better equipped to understand the diagrams of famous networks, like the 2 I showed earlier, as well as plan your own networks better. Finding our own kernel matrices and weights for this network took a lot of experimentation, insight, and a bit of luck. It would be infeasible to hand-tune the weights and features for any real-world network, but thankfully we can use gradient descent backpropagation to have our network learn what they need to be. This is the same algorithm that we saw in a traditional neural network. Each of our training inputs are going to bend and twist the activation curves of the many neurons to get them closer to our desired outputs. We'll repeat this process many times until those curves converge to something accurate. The process is the same, but the formulas will be a little different due to our ReLU and softmax activation functions. Additionally, the formulas need to account for kernel weights that are shared among neurons. Thankfully, many smart people have figured out these formulas and put them into various libraries. I enjoyed using Keras. An equivalent network to our spreadsheet network is accomplished with these lines of code. I've linked to a complete Keras example in the description. You'll find that these algorithms tend to find features that do not make sense to us humans, unlike our case where the features were clearly horizontal, vertical, or diagonal lines. In practice, if it finds features that work, even if we don't understand them, we tend not to mind too much. I hope building a convolutional neural network in a spreadsheet has strengthened your intuition behind kernel matrices finding features and assembling simpler features into more complex ones. With this intuition, you should be well equipped to build your own and solve your own image recognition problems. Happy learning.